most people interpret it. But people always kind of find slightly ways to go around it. So Gensen kind of decided to use more powerful methods that he could not prove were conservative over definitistic methods. So he uses transfinite induction and stuff like that to prove the consistency of arithmetic. And Hilbert himself came up with this idea that, let's invent proof theory. Let's consider the mathematical subject of proof theory, and let's see what can be proved with what. Kind of which methods lead to what things. And that's kind of the grandmother of reverse mathematics, which is still a big program going on, and kind of very interesting. Okay, so that's why when I kind of gave this talk in Strange Loop, I was talking about wartime proofs, because, Gödel kind of started in 1931 with the completeness, and then 33 or 32, I can't remember exactly which, with the incompleteness. And then Gödel himself came up with this notion of, this notion of trying to think about computable functionals of finite type, which is the famous system T. And his intention was to, it can be considered a liberalized version of the Hilbert program, but justifying the classical systems in terms of notions that Gödel wrote as being intuitively as clear as possible. Now, I don't know how much you know about how obsessive Gödel was, but apparently he kind of started thinking about this idea of functionals of finite type in the 1940s. In 1942, apparently, he kind of gave a Yale lecture about that. He produced a version in German that was published in 1958, and that's the so-called dialectical interpretation. And people always ask me, oh, it's about Marxism and stuff like that. No, it's not. His dialectic is just the name of the journal where the interpretation was originally published. And in 1974 or 75, he was still working on the English version of the paper. And he kept thinking about it. And I take that, the only things I know about that are in the collected works of Gödel, Volume 2, and there's a long explanation of all this, of how his thinking over that went, and I suggest you read there, because it has Professor Troostra from the Netherlands kind of spent most of his life working on explaining this stuff, and it's all very interesting. But I take that as a kind of evidence for what I was saying to you, that the Curry-Howard is something that's still in the making. We are still kind of getting to the crystallized version of it. And I put a later there, because I have some slides about that, but it will depend on how we're doing in terms of time, and we are not doing very well at the moment. Wartime proofs, mostly sequent calculus and natural deduction, and some people call the judgmental sort of calculus, like Brigitte was explaining today, natural deduction in sequent form, or some other people call it Martin-Liv version of natural deduction. And all these names seem to be fine. And as I was saying, they were all invented at the time of the Second World War, and the main proof systems used nowadays by provers, both humans and machines. Right. So how the programs get into it? Well, they get through Church because of the Lambda-Calculus, and they get through Curry because of the combinators and combinatory logic, which, as I said, had been precursed by Schonfinkel in the 1920s. And there's this very famous result that it's called the church thesis, so it's not really a result in mathematics as such, but it's this meta-logical result that lambda definability, recursive functions, Turing machines are all equivalent. So we have a good notion of computable function, at least for sequential computation, as used to be considered all computation. And as we saw, that's exactly what Brigitte was talking about this morning. How's this thing? Still working? Yeah, hope so. And these are the main things of logic forever, right? Mode exponents and hypothetical thinking, except that now we put a little pi there to remind you that this is also part of our universal discourse. You eliminate your assumption A, transform it into the assumption of the implication, but you keep track of what was the proof that you used to get the A implies B. And after the event, after people kind of thought about that and proved it in different ways, we can just add the terms for that, and then it starts looking like type theory, because you can have a term M of type A equals B and a term N of type A, and you can do M applied to N to get B, and you can use your variable X to abstract and get a function of type A equals B. And to me, that's the essential. Conjunctions and disjunctions are cute, but that's where the main stuff is. And the reason I'm saying that the stuff is not totally crystallized yet is because there's active areas of research on how to extend that. And that's some of the stuff that I want to discuss with you now. So effects, parallel programming, distributed computing are all active areas of research. So the question that I have for you to think about is how much can we extend Curry-Howard and still have something that is Curry-Howard? Because it's as usual in mathematics and in computing, it's a short blanket. You push one side, you cover your face and your feet are out, and you push to the feet and your face is out and you're feeling cold. So there's lots of design decisions that you have to make on how to extend this stuff. And in any case, you get a cornucopia of new logics and new program constructs based on the correspondence, but how good the correspondence is in each one of these cases is still up for grabs. So the point I keep trying to drive home is that category theory can help you with that. Because syntax is very loose. You can do lots of things with syntax. And you need some sort of guidance in which syntax is good for what. And I think category theory, because it actually was created to abstract from the whole of mathematics the essential structures, it tends to be good at seeing structure in computing. So what's category theory? It's a general mathematical theory of structures and systems, and the initial things that we need to know about are categories, functors, and natural transformations. It was initially suggested as a way of helping write algebraic topology and a homological algebra, and you can read some story about it, but I don't think there's a very good story written yet. And how does it get to be important for us? Well, it gets in because both Levere and Lambek, Joachim Lambek, came up with this idea that the same ways people were thinking about formulae as propositions and proofs as terms, we could think about the formulae or the types as objects in a category, and the terms or programs should be morphisms in the appropriate category. And notice the bold face there, because the appropriate bit is the hard stuff. And logical constructions should be categorical constructions, and most important of all, reduction should be proof normalization, which is the bit, that's why some people want to call it the Curry-Howard-Tate correspondence, because Tate was the one that showed that reduction is proof normalization. Now, as we were talking about at the beginning, it's kind of hard to kind of push this idea of triangles, of logics, Lambda-Calculi, and categories. You have to kind of have some idea of what is happening on the side of the categories. And Bartosz Milewski is very good at drawing these little kind of cute pigs, but the pigs can do so much. Eventually you have to do the calculations and the exercise. Last time I talked about that, I was talking to high schoolers, so I kind of decided that I needed to put at least the definition of a category. And I kind of hope here, I don't need to repeat it, but all the little diagrams on the side are kind of good enough, right? You have object, you have morphisms. For each object, you have an identity morphism. For each two morphisms that are in the correct situation, kind of where you have the codomain, or the first morphism is the domain of the second morphism. You need to be able to have a composition. And finally, that associativity of composition is essential, and identity with composition is just the thing itself. And, oops, did I go back instead of forth? That's not a picture for functors, sorry. I think I miscopied the pictures, because I wanted a big picture for functors, but the functors are, the point about functors is that they respect the composition, which is the main thing that we have in a category. Actually, there are two main things, identities and composition, and the functors have to respect both of them. So functor of an identity is an identity, and functor of f followed by g is functor of f followed by functor of g. That's a picture, yeah, cool. At least it's colorful, pink and blue. And then the natural transformations start kind of getting more complicated, even to draw little pictures, right? This is the traditional picture, nothing special, but you see, you have to start thinking higher order here, right? Because right now, there is a collection of A's, B's, C's, and all the objects kind of lying down here, and you have to have this kind of square for each morphism of your category. Nothing. So as Milewski himself says, you need many exercises to really get what this kind of yellow arrow there means. Now, what I said is that we wanted to kind of generalize notions of Curry-Howard. So we want to kind of think about categories, functors, and natural transformations, and you want to think about the constructions on our lambda calculus as being categorical constructions, right? And which categorical constructions? The first ones, the paradigmatic ones that Brigitte was telling us about, they are kind of easy because, you need to have products and sums, products for conjunctions, sums for disjunctions. You kind of, even the abstraction of the implication is a little bit more complicated because, as I said, you're going higher up. You're going higher order on that. So you need a notion of an internal home. You need to think about having in your category the collection of all morphisms from A to B, kind of represented by a single object of the category itself. So this is kind of slightly higher up. And then the things that we want to generalize from for, they take a lot. And some of the other things, maybe they don't really have anything to do with type theory or logic, right? There's lots of things that one can learn in category theory that might not be useful for categorical logic or for categorical proof theory. And so I say that this thing is a long time in coming, and it's still not completely there yet. And here's an example of what I mean. I mean, if you read only the bits without the red, then we are there already. That's something that Brigitte was telling you this morning, right? You have a formula A in logic, you have a sequent gamma proves A, which kind of, she has the same sequent, and we have the cut elimination rules that she kind of started showing you, because she kind of did cut elimination for introducing a conjunction and then eliminating the conjunction, and showed how this proof should be collapsed to a simpler proof. So here I'm showing, or actually Nicholas Gambino is showing, I just kind of copied from him, but we're showing a more complicated cut elimination rule, but you have the cut there, you're cutting this bang A with bang A on the other side, and you're kind of trying to say, okay, now if I introduce the bang A, and then I use it, I eliminate it by using a cut rule, I did not need that. I can simply map this whole derivation here into something of this shape, which just has the cut pushed higher, pushed to the things that I had before. And, you guys know that we can think about this business of rewriting proofs as rewriting in computer science, right? Rewriting systems of kind of with binders and stuff like that, but rewriting theory for this sort of stuff. And that's all very good and very traditional, and it's been with us since the 1960s. But then you want to think about, perhaps you want to think about much more complicated category theory. You might want to think about two cells. Instead of having the equations being this is equal to that, and I can transform this derivation, make that exactly equal to this other derivation, I might want to kind of think about rewriting, different kinds of rewriting, giving me different morphisms in the two category. And that's what is happening over here, where we are saying, what's the point of doing, instead of doing logic, doing category theory for logic? The point is that whenever you have a proof of A from gamma, and you name your proof. In my previous slide I named it as pi, for proof, but here I'm naming it as A. And then I have another proof, which is the same gamma proving the same A, but using A prime, right? And now I want to rewrite A to A prime, saying that this is an actual morphism in your category. Because, as I was saying, the point of doing category theory instead of logic is that you can name the different proofs of a single theorem A from a single set of assumptions gamma, right? It's not enough to say there is a proof, and there is a proof which is called A, and there is a proof that's called A prime, and I want to know how these proofs are related. Which one is the best proof? Which one is the normal proof? Which one is the more informative proof, or something like that? And that's why I say that category theory is important for people who want to do kind of programming. And then you have to start learning much harder category theory, I'm afraid. Not the little piglets sort of stuff, but this kind of stuff. Yes?
Are the two cells equivalent relations, or are they just like a single direction rewriting?
Sorry, say that again.
Are the two cells equivalent relations?
No, they are morphisms, right? When you see, this is one of the extensions of the notion of category theory itself. Instead of simply saying that a morphism is equal to another morphism, you might say this morphism is transformed into this other morphism via a two-cell, via a morphism of morphisms. And that's something that Anya will have all the pleasure to talk to you about tomorrow. So wait and you'll see better. But, see that that's why we can think that two-category is important. It's not just mathematicians trying to bamboozle you into learning more of their stuff. Okay, so why categories? That's exactly what I've been saying before, right? Model derivations and proofs, not whether theorems are true or not. Why is it good? Because modern derivations is useful in functional programming, linguistics, compilers, lots of other stuff. Why it's important? Well, this is just my take, but take it as you wish, with salt or not. It solves a problem where it's easier to solve and transport the solution to somewhere else. That's why I say that that the Curry-Howard is a useful thing for us to have. And, that slide was for mathematicians, so it also says that computer science brings new important problems to solve with our, in this case, mathematicians' favorite tools. So you guys will like it too. So the question I have for you is the one that's in tiny font there. I don't know if you can read it, but it's, why so little impact on maths or in logic? Why so little impact in industry? Because I spent the last 26 years trying to talk to people in the industry that they should pay attention to that. With little success, I must say. So, right. So which logics can we do Curry-Howard for? Here's a partial list. Intuitionistic logic, propositional logic, as we know, is the paradigmatic example. System F, polymorphism of a specific kind that was described by both Girard and John Reynolds. Dependent type theory, yeah, we can, but then, boy, we need kind of much more category theory than the little piglets can do, right? And yeah, kind of lots of disagreement on what is the best. I mean, their lab page on semantics of dependent type theory has 7 models, different models, and very few, this one is better than that because of this, and this one is better than that. Very little comparison. Sure.
Maybe this is your next slide, but what logics can category theory not model?
Good question. I haven't thought about this one. Okay, tomorrow, and you'll have at least partial version of an answer for me. Okay, I'm giving the game away, but what you cannot do is diamonds properly. Diamonds are kind of model logic, and you can do dependent box types, but I don't think you can do dependent diamonds. But, it's up for grabs, so maybe you sit down and do it then properly. That'll be cool. So, linear logics, several kinds of. Modal logics, as I was saying to him, sure.
About diamonds, does it have to do with the fact that diamonds are not normal, or is that, because that diamond seems to be problematic in other places too, like adjoint logic.
Value, I do not know what you mean by that, sorry. Say it again, try another version of the question.
No, that's all I have.
Well, you see, when you say value, I think you're thinking about things like the computational Lambda-Calculus, which has values and computations, and it's a monad, right? So that one category theory can do, because we have this notion of special kinds of monads that deal with values versus computation. So this dichotomy, very coarse dichotomy, right? Because there's lots of things in the middle, but then things get complicated again.
Yeah, my question was about diamonds is like not normal? If you've ever heard that term?
Well, I mean, I think of the diamonds as being possibilities. And there's a huge difference in logic between something being possible and something being true, right? And the modal logic itself is not very good, because lots of the modal logics that exist around us kind of make this identification between possibly false and false. So this is something that runs all over the place. And we don't want that. We want our methods to be able to differentiate things that are possibly false or possibly true from things that are actually true and actually false. So, I mean, wait until tomorrow, then we'll discuss that again. I don't. Okay, I'm sorry. Let's kind of see if we can. So, classical logic. Well, some people here kind of actually created the carry-out for that, but some other people don't like very much that carry-out because it doesn't have the categorical story is not very straight. It's a little bit doubtful and stuff. Or not doubtful, it's just that it's not as clear-cut as the intuitionistic or the constructed versions. So, you'll have to think. I bet you never heard of ecumenical logics, but that's kind of interesting too. It's a relatively recent thing also coming up from Kravitz in 2015. And it's this idea that, for certain things, for certain proofs, you want to pay attention on them being constructive or not. So, you want to construct proofs that at certain bits, this is a constructive bit. And this other bit, no, I kind of gave up and used a reduction of absurd, or I use excluded middle here or something like that. Sometimes you don't care if it's classical logic or constructive logic, but some other times you do. So ecumenical logics are logics that try to put the two systems in one bag. And it's not so easy, because normally when you put things in the same bag, the difference between the implication that's constructive and the implication that's classical disappears, and then we're just back into classical logic, where all this thing that I was trying to talk to you about, naming your proofs and being able to tell them apart, falls off. If you're not careful. Okay, one more. Go on.
Do there exist proofs for that can you convert intuitionistic logic to categorical logic? Is there a proof which can say that you can convert any intuitionistic logic to categorical logic? Or any other? Or is there a proof?
Well, let me tell you what I know and see if it helps you. What I know is that it's much easier to do this business of doing carry-out for logics that are constructive. They have this notion of associating functions to the proofs that happens much more naturally. When you try to do that for classical logic, there's several issues where this thing collapses completely. So the famous example is an example by Lafont in the Proofs and Types, where he shows that, you had a proof that gave you an A, and you have a proof that gave you another A here, and they're kind of just thinking to yourself that they're different proofs, but, if you kind of put the two together in a cut, and then you simplify it, then you end up either on this proof or on that proof. And that means that your cut elimination is not preserving the meaning of the proofs anymore, because you had to choose, and these two things were completely unrelated. So classical logic has this issue, and it's hard to deal with. People have done stuff, and I'm not the person to ask. You should talk to some other people in this room that kind of know much more about it. You can ask more after. Okay, let's see. So these are some of the logics, and yeah, kind of, I'm sorry, this is supposed to be, I think, to be aspirational for you guys. Kind of, so, we have linear Haskell. Rust apparently uses some of the ideas of linear types, or Campbell, kind of Rock, Isabel. All these guys kind of try to have notions of proof that are that can be modeled using category theory. And I'm just going to finish, well, maybe not, I don't know. I wanted to kind of look at some more pictures of a triangle. So, here you have the linear Lambda-Calculus with some linear categories and linear logic, and several different possibilities of linear Lambda-Calculus, which again we'll discuss tomorrow. You have model S4 Curry-Howard. So when I said to you over there that the problem was diamonds, I was not talking about S4 diamonds, I was talking about K diamonds, because S4 is already a little bit more better behaved than K. For S4, one of the things that Brigitte was talking about was this idea of introduction rules and elimination rules. And S4 does have a rule for introduction and a rule for elimination, both for diamonds and for boxes, for necessity and possibility. And this rules that existed since the 50s, they're not very pure. They're not very good in the sense they are not exactly like the rules that we had for conjunction, where you introduce the conjunction and you eliminate the conjunction, and you can see that that's all that you can do with that. The rules for box rules for diamond require the rules for box as a prerequisite, and even then you also need to. So I'll just write one small thing. The rule for introduction of box is this one here, right? Insequent calculus. So what I'm saying is that this rule is introducing the box on the right, but it's assuming that you already know what it is on the left. So this is not as neat, as pure as the rules that Brigitte was discussing this morning, but at least we have this rule and a similar one that puts a box on the left over there, so there's at least introduction and elimination. For diamond, much worse. It's only one rule, which goes like this for the diamond, for the box still. There's no elimination. You're introducing it both sides of the sequence, so it's worse. So that's why I say model S4 Curry-Howard works, and as far as I know, Nerode was the one who was kind of trying to do it in computing, kind of for hardware verification of all things. Bravis already did it, and Gavin Bierman kind of did all the calculations for that. Another system that you might not have heard of